All right, welcome back. We are starting a new unit here. We are going to be looking at the functions and relations. But today we are just going to be looking at interpreting graphs. Okay, so graphs could be a very powerful tool to represent and describe information. And as you can see, here is a graph, and it's useful because we can actually I can understand some stuff out of it. Okay, so let's take a look. So the first question asks, well, what does this graph represent, right? So here's the graph. What does it mean? Well, you can see on this graph, we have the mass here and the height here. Okay, so recall, this is the horizontal axis. That's the one on the bottom. This is your horizontal axis. Usually we call it the x-axis. And this is your vertical axis. And we usually call this the y-axis. Okay, so what does this graph represent? Well, here it says below is the graph of where each point represents a grizzly bear. Okay, so this graph represents the mass and height of how many? 1, 2, 3, 4, 5, 6, 7, 8 grizzlies. 8 grizzlies. Okay. Well, you can see each point represents a grizzly bear, and each point tells you how heavy, how much they weigh, and how tall they are, what their height is. Okay, so what does the horizontal axis represent? Well, the horizontal axis, again, is the x-axis, and that represents the mass in kilograms. Okay, now how do we figure out how much is each square represent? Well, you can see from here's the origin, right, 0, 0. From that point to this line right here, there is 1, 2, 3, 4 squares, right, 4 boxes. And that goes from 0 to 100, so each box is going to worth 100 divided by 4, which is 25 kilograms. Okay, so 100 divided by 4, again 4 because there are 4 squares between 0 and 100. So 100 divided by 4 is 25 kilograms. What does the vertical axis represent? Well, the vertical axis says here it represents the height, right, in meters for each of those grizzly bears. Okay, in meters. Each square on the vertical axis is equal to how much? Well, let's see. So again, this is 1 meters. Now let's count how many squares there is between 0 and 1. That's 1, 2, 3, 4, 5. So it's going to be 1 divided by 5, which is 0.2 meters. Okay, so that's how much each square is worth. Okay, it's worth 0.2 meters. Okay, now which bear is the tallest? Well, if we're looking for the height, then we're looking at the y-axis. We want to see which one's the tallest, so we want to see the point that is, the one that is highest up, right? And that is G. G, grizzly bear G is the tallest because you can see this gives you the maximum height right there. And what is this height? Well, each box is worth 0.2, so that's 3. So 3 minus 0.2, that would be 2.8 meters. Okay, of course it doesn't ask, but that's what it would be. Which bears have the same height? Well, there are 2 points that have the same, 2 bears that have the same height, namely C and F. C and F, right? Because they have the same y value. Okay, same y value. And what is this? Again, that's 2. So that's 1 square above it. So you just add 0.2 to 2. So that's 2.2 meters. That's how tall they are. Which bear has the greatest mass? So if we're looking at mass, then we're looking at the horizontal axis. And we want the greatest. So we want to look at the point that is furthest to the right. So that is this point right here, H. Okay, so the grizzly bear H would be the heaviest. And how much does this bear weigh? Well, that's 500, and that's 1 square after 500, and we know each square is worth 25. So this will be 525 kilograms. It's pretty heavy. Now, what is the mass of the second shortest bear? Well, the second shortest bear would be bear B, right? Because that's the second lowest point. And what is the mass? Well, if you're looking for the mass, then you go down to this point, and that looks like right in the middle between 100 and 200. So bear B and with 150 kilograms. Okay, so again, you can see based on a graph, we can actually get a lot of information from the graph. Okay, so that's just one particular example. Let's take a look at another example here. Now it says here to the right is a graph of the cost of hiring a plumber to come to your house. The plumber has an initial call-out charge as well as the hourly rate. Okay, so call-out charge means once they step out of their house or are out of their workplace, then they actually charge you money. Okay, so even though even if they arrived and then you told them, oh, actually nothing happened, everything's fixed, they will still charge you money because they step out of their their initial place. Okay, so that's what we call the call-out charge. Once they accepted the job and they come, then they charge you money. Okay, so that's the call-out charge. Hourly charge, of course. So the longer they work, then they charge you money for that, right? For each hour. Okay, so what does vertical axis represent here? Well, it represents the cost. My vertical axis represent not cost. It represents the cost. Oh, let me just call it the total cost. Okay. Horizontal axis is the time. Okay, it represents the time in hours. Okay, the total cost in dollars. Right. Okay. How much does it cost for just the call-out charge? So you can see this point would tell you the call-out charge because you can see this point happens when time is 0. Okay, when time is 0, it shows that the charge. Okay, well actually, first we need to figure out how much is each point worth or each square is worth. This is 0, so from 0 to 100 it takes 1, 2, 3, 4 squares. Okay, 4 squares. So each square divided by 4 is going to be $25. Okay, $25. So that's one square above 100. So the charge for the core charge is 125. Okay, if the plumber works for 1 hour, how much is the total cost? Here's 1 hour, and the total cost is this point right here, and you can see that it is $200. Okay, that's $200 right here. What is the total cost for 2 hours of work? Well, 2 hours of work is right here. That's this point. And this would be the cost. And again, we know each square is $25. That is one square below 300. So we go 300 minus 25, which is $275. Okay. Now, the next question says, well, how much does the plumber charge per hour then? Well, you can see for 1 hour, it costs $200. For 2 hours, it costs $275. For 1 additional hour, it charges $75 more. And you can see that from here, the core charge is $125. So that's for 0 hours of work. And then for 1 hour, right, after 1 hour, the cost becomes $200. So you can see for each additional hour, the charge is $75 more. So what that means, the hourly rate for the plumber will be $75 per hour. Okay, so you can do it like this. This is $200 for 2 hours, sorry, for 1 hour, and well, call charge, that's no time, right? That will be divided by, this again is 1 hour of work minus the 0 hour of work. So this tells you how much more, and this tells you how much more time, right? So that will tell you the hourly rate. So this is $75 per 1 hour. Dollars per 1 hour. Okay, so we can see this is the difference in the price, the cost, and this is the difference in time. And if you divide them, that will tell you the charge per hour in this case. Okay, so then finally, what is the cost for hiring the plumber for 9 hours? You can see 9 hours is actually outside of this graph, but we can still calculate it because we know the initial charge is $125, right? So let me write this out. Total cost. We know the initial charge is $125, plus we know each hour is going to cost $75. and we are going to hire this plumber for 9 hours. Okay, so 125 plus the 7, so this again is the co-hour charge, initial charge. This is the hourly rate, and this is the number of hours. So this will tell you the total cost. Okay, so then let me see here. That's 125 plus 75 times 9 is, what is this? 675. Added together, it is going to be $800 for 9 hours of work. Okay, so that would be, again, you can see just based on this graph, you can actually estimate, or actually not estimate, you can predict or precisely how much it's going to cost you when you hire a plumber for 9 hours or even more, right? So again, the graph actually tells us a lot of information, okay, if we can read it properly. Okay, so again, here it says in math, graphs can give you a wealth of information. Let's look at this graph that represents the day trip from Burnaby to Bridal Falls. Okay, so you can see here on the x-axis or the horizontal axis, it represents the time, and on the y-axis or the vertical axis, it represents the distance. Okay, so distance from Burnaby. Okay, so it's the distance from Burnaby. Okay, now here it says the first question: how long did it take to make the round trip to Bridal Falls and back? So this is the round trip. So from Burnaby back to Burnaby, right? That's why and you can see this goes to Bridal Falls and come back to Burnaby. Okay, that's what the distance increases and then decreases, because this is the distance from Burnaby. Okay, distance from Burnaby. Okay, so here, how long does it take? It takes 10 hours. Okay, so again, from A to H, it takes 10 hours. Second question says, how many hours did they travel before their first stop? Okay, now you might ask, well, where's the first stop? Well, the first stop is actually a B to C, because you can see the distance did not change from B to C. However, time does go on, right? Of course, time always goes on. You know, it just continues to go on regardless. But you can see the distance is not changed, so that means they are stopped. Okay, so how many hours did they travel? Well, from A to B, it takes 2 hours. Oops. So they travel 2 hours, and then they stop for some time. And it says how long, well, the next question says how long was the shortest stop? Well, that's a stop, right? Because you can see the distance did not change. Here is another stop, and here is another stop. Now, that would be the shortest because, well, you can see the line segment is the shortest. Now, how long is that going to be? Well, F, if you go down, is going to be at 8 hours. And G, if you keep going, draw it downwards, it stops at the next line, and that is right in between 8 and 10, which means this is going to be 9. So how long was the shortest stop? Well, it was 1 hour. Okay. What was the furthest distance? Traveled before stopping? Okay, so the furthest distance traveled before stopping. So again, that means we're looking at two pieces, right? This portion, that portion, that portion, and that portion, right? Which part would have the furthest distance before stopping? Okay, so again, there's the stop. That's why that's one piece. That's a stop. So that's a distance traveled. That's a stop, distance traveled, and obviously when you return home, you stop. So it looks like this one would have the furthest distance, right? Because that is the longest line. Well, what is the distance then? Well, from C, if you draw to the y-axis there, this would be the 30 kilometers from Burnaby. At D, that looks like, okay, so here's 100. Now let's see, how much does each little square represent? Well, again, that's 20, and that's 1, 2, 3, 4 squares. So 20 divided by 4 means each square represents 5 kilometers, okay? So D is right here, and that's 100, that's 105. It looks like actually it's a little bit more than 105, because if you zoom in, you can see this line is actually just above that square. So I'm just going to call it 106, okay? clearly here we're just estimating, okay, because we are not sure, where that line exactly it is, but we'll just say it's on 106. That'll be a good estimate. Okay, which line segment represents the fastest speed and how fast was it? So if you're looking for the fastest, then you're looking for, uh, a long distance in a short amount of time, right? So really you're looking for the steepness of the line, right? The steeper it is, that means, you go far, and it means it's a short amount of time, right? So the steepest part of the graph would tell you the fastest speed in this case. So the steepest line, it looks like it's either from C to D or G to H. Okay, I'm not 100% sure which one is the steepest. So let's just try and figure out which one is the steepest. Now, how do we tell? Well, we can find the speed, right? Just like what we did in the previous page, to find the cost here, what you have to do is find the change in this case, change in cost divided by change in time. So here we can do the same thing, right? To find the speed, you can go change in the distance divided by change in time. Okay, so speed, you might have learned this from science already. I don't know. You'll learn it in math, science 10 for sure. Speed is just the change in distance divided by change in time. Okay, so for C to D, well, this is 30, and that we know that's 106. So we're gonna say 106 minus 30. Sorry, not 60. So that would be the change in distance, right? From 30 to 106. So 106 minus 30. That would be the change in distance. Well, what's the change in time? Well, C is at 4 hours and D is at 5 hours. So that's 2 minus 1. That's the change in time. So that's 76 divided by 1. So that's just 76 kilometers per hour. And let's look at GH. From G, this has a distance of 60, right? And at H, the distance is 0, right? From home or from Burnaby. So it's just going to be 60 minus 0 divided by, what's the change in time? This is 9 hours. And at H, that's 10 hours. So 10 minus 9. So this is 60 divided by 1, which is 60 kilometers per hour. So which line segment represents the fastest speed? Well, C to D, CD, line segment CD represents the fastest, and the speed was 76 kilometers per hour. Okay. So again, from this graph, we could actually extract a lot of information out of it. Okay, we can find the speed, right? And yeah, okay. So here's the practice. Another question here. And it says Johnny decides to go on a trip with his motorcycle and leaves from school. Describe what is happening in each line segment. So here is the gas in the tank. And this is the time from start of the journey in hours. And here's the volume of gas in a motorcycle. Okay. So for each line segment, I actually want you to think what it could mean, and maybe write a sentence about what could happen. Okay, so we are gonna do A to B, B to C, and D to E. Okay, so think about it and see if you can write a sentence about each line segment. Okay, from A to B, you can see the amount of gas, right? The volume in gas in the motorcycle is decreasing. So what does that mean? Well, if the volume is decreasing, that means, well, he's on a bike, right? So Johnny rides the motorcycle, that's right, motorcycle. Oops, forgot a C, motorcycle. I don't know, maybe he went to well, actually, this is a good point right here. Where did he go, right? If you think about B to C, what happened here, right? You can see the amount of gas in the motorcycle increased by a lot in very, very short amount of time. What does that mean? Well, it means he went to the gas station, right? So Johnny rides the motorcycle to the gas station. And that leads us to B to C. And what happened? Well, he filled up the gas tank, right? He fills up the gas tank. Right? That's why the amount of gas increased by a lot in very short period amount of time. Okay, but A to B, you can see the amount of gas is decreasing, right? Decreased, therefore he was riding on a motorcycle. Okay, finally for D to E, well, the amount of gas did not change. Well, the only thing that could happen is he was resting, right? So maybe he, I don't know, drinks, or maybe not drinks. He, studies at a coffee shop. Again, obviously, I'm just making up stories. It could be anything, but clearly he was not moving, right? That's why the amount of gas stays the same. Okay, he was not riding the bicycle. Okay, he was not riding the bicycle. So I'm just saying, well, he's studying. Okay, or he could be drinking coffee. He could be having a dinner, right? Anything could happen. All right, so hopefully that makes sense. The last example I'm going to show you here is, well, now we've been reading the graphs. How about let's make up a graph, okay? Let's draw a graph. So sketch a graph from given information. Here's a Sam walked his normal pace toward a corner store. On the way, he met a friend and stopped to talk for a few minutes. He then continued his way to the store at his normal pace. After arrived at the store, Sam bought groceries. He realized he had taken too long and walked home at a faster pace without any stop. Okay, we want to sketch a graph of the Sam's trip to the store with distance from home versus time. Okay, so again, the y-axis represents the distance from home, and the x-axis represents the time. Okay, so he's going to start from home, right? That's where he starts. That's the distance from home. Now, the key here is normal pace, okay? And we have, again, another normal pace. So let's just say his normal pace is this fast. Okay, so he walked his normal pace to the corner store. And we're going to assume that he's just walking closer and closer to the corner store. Okay, he doesn't make a detour or anything like that. Okay, so he walked his normal pace to the corner store. On the way, he met a friend and stopped to talk for a few minutes. Okay, so he stopped, which means the distance from home remained the same, right? Because he stopped. Therefore, it should be a horizontal line. Okay, I'm just sketching without a ruler here. Okay, so that should be a horizontal line because he stopped. The distance remained the same. He then continued his way to the store at his normal pace. So what does that mean? Well, I think we saw earlier in this example, right? The steeper it is, it means the faster it is, right? So if it's the same pace, that means the steepness of the line should remain the same. So if it's a normal pace, that means the steepness of that line should be the same as this. Okay, so I'm just going to try my best and then try to replicate the same steepness of this line right here. Okay, so that's, okay, well, that's too, I'm just going to say that, okay. After arrived at the store, he bought groceries. So that means the distance from home will, be the same because he's at the store for a while. He realized he had taken too long and walked home at a faster pace. Okay, so again, this is a faster pace without any stop. Okay, so faster pace means the steepness of the line should be steeper. Okay, it has to be steeper. So I'm just gonna say he ran home, woo, like that. Okay, so you can see this is a faster pace because the steepness of the line is, well, greater. Okay, so that's the lesson for today. You have practice questions to do. Hopefully, this is not too bad, right? Reading the graph and understanding the graph and get information out of the graphs is not too bad. And, making graphs from the given information. Again, let me know if you have any questions. Okay, otherwise, good luck.